In the Sofia balloon experiment, we brought a helium balloon on board along with a plumb bob, a pendulum, and we wanted to see what would happen to both of them during takeoff and during landing. So let's see. And so here is a picture of our setup on takeoff. And so to orient yourself, the front of the plane is to the left. And so we're sitting on the runway, the plane is going to accelerate toward the left, and what is first going to happen to the pendulum that you can see hanging here from the table? Is it going to keep hanging straight down? Is it going to hang off to the left? Or is it going to hang off to the right while we're taking off? So come up with your prediction, and then we'll check it out by seeing the video of the experiment. Well, what about the balloon? And so the balloon is hanging pretty much straight up and down here. And is it going to continue to float straight up? Or is it going to lean off to the left or off to the right? And so come up with your prediction, and then we'll see. And so this is the video during takeoff. Now there is a lot of vibration. And so you're going to see the pendulum swinging back and forth, and the balloon is being buffeted by some air currents in the cabin. But I think you can see overall what happens to the balloon. It tends to be off to the left, and the pendulum, which is swinging back and forth, tends to hang out over here on the right. So if you said the balloon would hang to the left and the pendulum to the right, you were correct. But it's okay to not be able to predict this, especially the balloon's behavior, kind of mysterious. Notice her papers behave more like the pendulum. They slid off going to the right. And so we want to be able to explain this using some physics. And so first, the pendulum. And so the pendulum needs to accelerate to the left with the plane. And we need a force to do that. And this force must also act in the same direction as the acceleration. Newton's second law, sum of the forces equal sum of the forces equals ma, and force and acceleration are both vectors. The net force and the acceleration have to be in the same direction. And so gravity can't be the force that causes the pendulum to accelerate. It's acting vertically. And so we need something to the left, and that can't be tension either in the string if the pendulum is hanging straight down. But if the pendulum is hanging in this direction, there's a tension pulling up at an angle, and there's a vertical component which is supporting its weight, and a horizontal component that is causing the acceleration. And if you know how to apply Newton's second law, you should be able to show that the acceleration of the pendulum, and therefore also Sofia, is given by the equation g tangent of this angle. But since there's a lot of fluctuation in what that angle is, it would be difficult to get good agreement with the acceleration of the plane, although I think you could if you chose carefully. And we will talk a little bit more about how that derivation is done. You might pause and see if you can show that on your own now. How about the balloon? And so the balloon did the opposite of what the pendulum did. And so there are various ways to explain that. One is thinking about the air in the cabin. And so the air in the cabin also has to accelerate to the left. And we need a force toward the left causing that. And that force is from the bulkhead that separates the cabin from the Sofia telescope. And so the bulkhead pushes on all of the air to make it accelerate. But let's say here, this air in front of this line, to the left of this line, is being pushed by the air back here. So this air, there's not as much mass, so I don't need as much force to cause it to accelerate. So the pressure is actually less here than it is here because the bulkhead has to push all the air. Here we only have to push some of it, here even less. And so there's a pressure differential, or what you might call a pressure gradient, where the pressure is high here and low here. And what does a helium balloon do? Well, it floats. It goes from high to low pressure in the atmosphere. Well, we're sort of creating a sideways floating here, a sideways buoyancy. And so that is what also causes it to go sideways. Well, what about during landing? So if you had trouble making your predictions before, let's see if you can do better. And so the acceleration now is going to be to the right. And so Sofia is gliding into the runway. It is slowing down gradually, but when it lands on the runway, the brakes are applied and the thrust reversers, and there's a large acceleration to the right as the velocity of Sofia decreases. What's going to happen to the pendulum? Is it going to continue to hang straight down, hang to the left, or hang to the right? And again, the front of the plane is in this direction. And what about the helium balloon? Is it going to continue to float straight up and down? Is it going to hang to the left or over to the right? What do you think? Remember your prediction and we'll find out. And so here, again, there's some air currents and some vibration. We're coming in about there where you saw the shaking. There's a large acceleration now, and there's some shaking around, but I think you can see the helium balloon tends to be to the right now, and the pendulum tends to be to the left. And so again, the pendulum's behaving as you might think other things would. Let's say there was an unsecured water bottle on a table, and you are braking as you're moving to the left. What might happen to that? Oh, it did happen. And so the pendulum behaves more like the water bottle, the helium balloon in the opposite. And so hopefully your predictions worked out better this time. The pendulum swings to the left because we need a force to cause the acceleration to the right. And the only force is this horizontal component of the tension. You have weight acting straight down, so that can't have a component in the direction of the acceleration, but you have this tension vector that does have a horizontal component. We said before we could figure out what the acceleration is of the pendulum, and hence also Sofia's acceleration, at least assuming that this was in equilibrium here. And so let's do that real quickly. We want a coordinate system. And so y is the vertical plus x to the right and horizontal. And if we look in the y direction, there's no acceleration, so the sum of the forces equals 0. And the only forces in the y direction, I have weight. I could have drawn that a little better, but that's exactly in the vertical and negative. And then I have this component of the tension, and it's adjacent to theta. So adjacent would mean the hypotenuse here, t, times cosine theta. And then minus the weight, that's the sum of the forces equals 0. And then we can look in the x direction, where we have acceleration, and I'm making it to the right, the direction of the acceleration. And the only force in the x direction is the opposite side of the tension vector triangle here, so it's the horizontal component, so that'd be t sine theta. And I have two unknowns, the acceleration and t, but I can take this equation and solve it for t. I get mg over cosine theta, and I can put that in the tension here, so I get mg sine theta over cosine theta equals ma, and the mass divides out on both sides. And you might know that sine over cosine is equal to tangent. So I get g tangent theta equals the acceleration. And so you might try going back to that video and seeing if you can measure an angle, but again, the little bit of vibration makes that hard. And then the balloon, we also explained this, but now it's during braking. And so there's a net force on to the right on the plane, causing an acceleration to the right so that it slows down. And the air in the cabin of Sofia also needs to slow down, so we need a force to the right. and that is produced by the surfaces of the front of the plane pushing back on the air. And if you drew a line here, what's causing this air to accelerate to the right will be this air pushing on it, but there's not as much mass here. So the force is not as much here as it is here. And there's a gradient, a differential in the pressure where we have high and low. And a helium balloon is going to feel a buoyant sideways force, just like it feels a vertical force in the air where you have high pressure down here and lower pressure up here. And so it causes it to also float sideways. We also did another experiment with the balloon. We just observed this. So this is David holding the balloon when we're on the runway, and you can see how much air or helium is in there. What's going to happen to the balloon when we're up in the stratosphere? Is it going to get smaller, larger, or stay the same size? And here's what happened. And I think you can see it got significantly larger. And so it did get larger. And why is that? Well, up in the stratosphere, the air pressure is less. Fortunately, we weren't experiencing that because we're in a pressurized airplane, but they pressurize it so it's about at the same air pressure you would experience if you were on an 8,000 foot high mountain, 8,000 feet above sea level. And so that is lower air pressure than what was on the runway. And so the helium can expand more. Looking at exactly how that happens at the molecular level is pretty interesting. I recommend you do that in your chemistry or physics class. But it did expand, and we actually were worried it would pop. And so when we purchased the balloon, we had them not inflate it all the way to start with. You can see it's a little off. You've probably noticed something like this happening maybe with a bag of potato chips. If you drove up to the mountains, it will expand. And David thinks that his head expanded too. If you look at his picture here on the runway and here, that might have something to do with it. I think it's more due to being up all night on our Sofia mission.